So this feature is one of the, again, great Power PMAC feature. It's called Special Lookahead. Remember, Power PMAC always looking one move or two move ahead, like in the blending mode. So it blends in the other mode, calculating the next move ahead. With this special algorithm, it can look more moves ahead. Depends on your size of the definition of this look ahead buffer. It can look ahead more segments, and that gives you the advantage of checking the velocity acceleration violations of the path of the trajectory. This algorithm computes several moves ahead in motion programs. It checks for violations of the motor limits. So if you have the velocity limit of the motor with the motor x dot maximum speed and your acceleration limit motor x dot maximum inverse acceleration limit, so it will check for these violations through the trajectory, the path. Once you set this motor, also you can check the position travel limits with your software travel limits. Negative limit with the motor x dot min pos, and the positive limit motor x dot max pos. So it will check these limits. Here it mentions the jerk limit, but you can cross this one. This is a typo here. It will check only for this position limits, velocity limits, and the acceleration limits. So what happens if the violation detected? You have the trajectory and you define this buffer, and it find a problem point. At that point, for example, one of the motor's velocity is violating. It's calculating, more than it's supposed to, your limit. And then, if that is detected, the motion is going to slow down at that problem point without altering the position trajectory. So, since PMAC looking ahead and finding that problem point, it will slow down up to that point to not violate that velocity problem or acceleration problem. This algorithm recalculates the motion leading up to that problem point to keep all motion within the limits. Lookahead permits acceleration and deceleration over multiple blocks. These are, the position, the blocks, your commands. Lookahead permits automatic deceleration into a tight corner and acceleration out of that corner. So it's like driving a car and taking a right turn. So you have to decelerate and make a right turn and then accelerate to yield to the path, right? So it's like, for example, the good example, which we will also execute, you have Y, you have X. These are your motor 2 versus motor 1. If you have a path like this, so this is a problem corner, right? So this is the tooltip. Let's say this is the tooltip, has to follow this path. The X will go, when it goes here, the Y will be accelerating velocity, right? So at this point, it will violate Y velocity because it's going to keep going to that point. This is one point, starting point, this is the end point. So the Y will be accelerating, but it should, slow down at this point to be able to make that corner. So when X is going like this, Y will be, slowing down in here to be able to make that point, and then continue, accelerate from that point to come here. So with this algorithm, we will be able to find that point ahead and slow down the y velocity. So how can we set up this lookahead buffer? We have some steps we need to go through. Starting with the step 1, set motor x dot maximum position and minimum positions, right? These are the software travel limits. And these are in motor units for each motor in the coordinate system relative to the home position. And then you need to set the maximum speed motor with the motor x dot max speed. This is motor units per millisecond. If your feed rate is lower than the motor maximum speed, then your limit will be the chord x dot maximum feed rate. If you set the f less than this motor maximum speed, then your limit is the chord x dot maximum feed rate. Then you will set the acceleration limits, right? So set motor x dot in a max, inverse maximum acceleration in milliseconds squared per motor units. Then this is very important. Without this, lookahead will be not on. So you need to set the segmentation time, chord x dot seg move time. This is in millisecond. For perfect trajectory, you want to set this as low as possible to make more segments. We know what it is, right? Power Pmax, when the interpolation, it gets divided into segments with this time and make a fine interpolation in between. So tighter this time, it will be better the trajectory. So the typical values are like 2 to 20 milliseconds. This depends on your usage of the CPU. If you're using a full CPU time, then you don't want to go with the lower values. Maybe you may run into a runtime error. So you need to make that compromise later on. After setting this one on, setting, for example, 5 or 10, now you can turn on the lookahead. But we need to find out first the lookahead buffer size. So we need to calculate that. First, you need to calculate the maximum stopping time for each motor in the coordinate system. So that is done by motor x dot max speed times the inverse acceleration limit. Or if your maximum speed is the chord x dot max feed rate, then you times with that inverse of the acceleration. So that will give you the stopping time. Now select the motor with the longest stopping time and then compute to chord x dot lookahead distance, LH distance. So this is the one you want to calculate it. And we have a formula in the next slide. I'll show you. Once you calculate this one, you can compute the total number of segments and define the lookahead buffer. The reason this is, you can set this one as your lookahead buffer size. This is the minimum size you need to set it. So, for example, if you have the blocks like this, and the program goes through like that, right? With this lookahead distance, you can look ahead all the way to here, but some wants to come back, reverse the direction, retrace the trajectory. So you want to go, and then if you want to go back, then you calculate the total number of segments. So lookahead distance plus the retrace backward size. We will look into that too. Once you calculate that the total number of segments, now you need to delete the lookahead buffer and define the lookahead buffer. So about segmentation time, all linear circle and PVT mode trajectories are created by computing intermediate segment points with a coarse interpolation algorithm every chord x dot seg move time in milliseconds, and then executing a fine interpolation with a cubic spline algorithm each servo cycle. So segmentation move time is a floating point number, and it's in milliseconds. If it's set to 0, the lookahead will be not off. You need to turn it, if you want to enable the lookahead function, you need to set it to greater than 0. We mentioned about the smaller the value, the tighter the actual motor position, will be better trajectory, but then it will take more computational time of the CPU. So if PMAG run out of time, if you set it too low, and if it's run out of time, it will trip at runtime error. So if you ever run into a runtime error issue, one of the first register you want to check is the structure you want to check is the seg move time. Okay, let's calculate how much lookahead needed, the lookahead distance. So remember, we needed to find the stopping time of the motor, right? Compute the largest stopping time for each motor in the coordinate system, obtained by the maximum speed times the maximum inverse acceleration. Once you find that, now divide into that time to 2 times the coordinate chord x seg move time. Then you find the segments needed. Once you find the segments needed, the formula is chord x dot lookahead distance is equal to 4 times segments needed divided by 3. And if you put all this together, the final formula will be this 2 times the motor x max speed and motor x dot inverse A max divided by 3 times the chord x dot seg move time. Size the lookahead buffer to hold this number of segments plus the number of segments through which one desire to reverse. So if you want to go, you go in this direction, and if you want to come back, you want to have the retracing ability, then you need to add reversal buffer. So an oversized lookahead buffer provides history of trajectory. Position information in buffer is reversible, unlike the motion program. Remember, in motion program, it's line by line. It's getting executed line by line. So you start from open program 1, and then until the end, the close, it's executed line by line. There is no way, before the close, you can go back, in the opposite direction. But in this case, you can, because you're defining a reversal history by, oversizing the buffer of the lookahead. And if you do so, you can go with this less than comment in the if you want to reverse the path, you can use this less than comment to go back in the trajectory. The reverse operation obeys same limits as forward operation, so it will still be checking the violations of the motor. acceleration and the velocity and the position. Can only reverse in continuous blended sequence. Quick stop in either direction with the / command. Forward operations again by the greater than sign or run or step command. Seamless continuity into new parts of program. During the reversal path or the forward execution of the reversal path, you cannot do the M variables. No synchronous M variables will be executed. You cannot use this; they will not be executed. But however, you can use the synchronous label assignments with this chord x.nsync. These will be executed in the reverse and forward directions, so it's possible to monitor the program move block being executed if synchronizing line labels have been used in the program. The reverse segment, calculation of the reverse segment, which we show it with the NR, is equal to reverse distance in motor units divided by the largest motor maximum speed of the coordinate system times the segmentation time, chord x.segmove time. So you can calculate the NR, reverse distance, and then you can add that one to look at the chord x.LH distance. Then you have the total number of segments you need. So once you find the total number of segments, now you can define the lookahead buffer. It's very easy. You just issue the command define lookahead and the number of the segments you want to size. So for example, if it's 2000, you say define lookahead 2000 and download to the controller. So this NT can be a 32-bit integer representing the number of move segments that can be stored in the buffer. It must be at least 1024 or greater. So you cannot define less than 1024. It should be at least 1024 or greater. So if your calculation come up to be less than 1024 for the NT, you should at least define for 1024. And so it can be also at least as coordinate chord x.LH distance to cover the desired lookahead without the retrace capability. And this is important because lookahead buffers are not retained through a power down or reset. This command must be issued after every power up or reset. So you can include this define lookahead command in the pp startup.txt for automatic execution every power up. Okay, what if you want to delete and define the buffer again? You can do it like this. You have to, if you want to define a new buffer, you need to first delete that buffer and then redefine again after the change. So you can delete the lookahead for coordinate system 1. Coordinate system 1, delete lookahead, and then you assign a new motor to an axis. &1, motor 4, for example, assigned to a C axis, and now you need to define the lookahead again. &1, define lookahead 10,000. Power PMAC, however, can support a change between the rotary positioning axis and the spindle axis without the necessity to redefine this lookahead buffer. This is for NC applications. You want to use one of the motor as a spindle. So if it's assigned as a rotary position axis, you can make a spindle axis without doing this thing. And when a motor is assigned to a position axis, it's involved in the lookahead calculations. That means it's checked for the violations. But if it's assigned as a spindle axis, it's not. That's the difference. Because spindle, you don't need to check for the maximum, the speed, because it always turns on the one speed you want. Okay, this is the example. It's this one actually. So it starts from 0, 0, it goes to 10, 10, and then 0, 20. This is the setup and definitions without the lookahead and with the lookahead. So we're going to execute that profile without the lookahead and with the lookahead. These are the definitions for it: the TA, TS time, TD time, maximum speed, all that, and the segmentation move time equal to 0 for without the lookahead, right? And when you want to turn it on, you want to download this one on top of this. So see, segmentation move time equal to 5 now, and we calculate this lookahead, the chord x dot lookahead distance. It come up like less than 1024. So we defined 1024 at least. So define lookahead 1024 for this example because the NT calculation was less than 1024. So once we run with the lookahead, this little program here, so it's same as this profile. Homing motor 1 and 2, linear absolute mode, starting the gathering with the 50 F feed rate 50, X10, Y10, X0, Y20, same profile, and then stop the gathering. And then when we plot it, this is without the lookahead. Okay, let's explain it here better. This is motor 2, right? And this is motor 1. So if you look at the velocity profile of the motor 1, it will be something like this. This is the Vx, and this is the Vy. So this will be the Vx. You go here and come to the 0. And the Y will be, continuous. So it will be like this. That will be the Y. That's Vy. This is Vx, right? So when you run with the lookahead, see there is a dip in the motor 2 velocity profile. So at that point, it's actually, more than it's supposed to. So with the lookahead, when you turn it on, this second motor velocity will dip like this. Other than straight, it will dip like that. Right here. So motor 2 slows down for the corner, but the identical position trajectory is executed in the shorter time without violating any constraints. Make sure you put the motor 1 commanded position and motor 2 commanded position on the left axis, and motor 1 commanded velocity and motor 2 commanded velocity on the right axis, and versus time. So you need to open the plot, make sure you have these motor 1 and 2, and then the motion program automatically gather the data, so you just upload and plot the data after you finish.